Hi everyone, today we are going to talk about how you can solve these simultaneous linear equations or systems of equations with two variables using the substitution method. So far we've only talked about one method, the graphing method, and we realized that it's not the best because once you have answers that aren't integers or whole numbers like fractions and decimals, it's not very accurate to use the graphing method unless you're using a graphing calculator or a online tool. So for instance, if the answer was 8/3 negative 5/3, it's kind of hard to tell whether you have a precise answer with the graphing method. So there is an algebraic method that's called the substitution method. And you don't need graph paper, you don't need a ruler, you just need pencil and paper and your brain. And you'll get an accurate answer at the end. I'm going to work on two examples from the book with you. But before we get started, I did want to talk about the steps to using the substitution method. There are 5 main steps. First, you have to choose one equation out of the 2 or 3, whatever, to isolate either variable x or y. And usually you'll see a loner variable that's kind of all alone and it doesn't have a coefficient attached to it, and doesn't have a number multiplied to it. Secondly, after you've done that, you're actually going to isolate it, and then you're going to substitute its equivalent expression into the other equation. After you do that, you'll solve for whatever remaining variable is left over, because the whole point of doing that, of isolating that variable and then substituting, is to get it down to one variable. You'll solve it like a normal equation. You'll get the value of x or y, whatever is remaining. Then you substitute that variable's value into either equation will work. Then you can check your solution by substituting both values into both equations. So make sure that you have these 5 steps jotted down in your notebook, because I'm going to be honest with you, substitution, there's a lot of substituting back and forth, so it can be kind of confusing. Usually I'll see people label their different equations, or they use different colors while they're working. So as you're working, you might want to decide on what works best for you. All right, let's get started then on this first example. It says that we need to use the substitution method to solve the simultaneous equations x plus 3y equals 8 and 2x plus 5y equals 13. So remember, our first step is to isolate a variable. It doesn't matter if it's x or y. However, we're looking for a variable that is a loner. It doesn't have a coefficient attached to it. There's no number being multiplied next to it, because it's going to make our lives much easier later when we isolate it. So you probably figured out in this situation, it's going to be this first equation because it has an x that is all by itself. So we're going to go ahead and we're going to isolate that x, meaning we're going to separate x from the rest of the terms in that equation. So instead of x plus 3y equals 8, I'm going to get x by itself. I can do that by subtracting 3y on both sides. Now be careful here, because even though these two are like terms with each other, 3y and negative 3y, and they cancel each other out, leaving x on the left-hand side, this 8 and this minus 3y are not like terms, so we cannot combine them. We're just going to copy them back down and make sure that they are separate from each other, because one's a constant and one has a coefficient attached to a variable, and we're just going to keep it like that. So here we have isolated x. Okay, so I'm going to write up here that we isolated x. We got x on its own on one side. The reason why we like that and we want to do that is because later we're going to take this information right here x equals 8 minus 3y, and we're going to substitute that into the other equation, okay? So I'm going to take this other equation now. This was step 1. I'm going to take the other equation, very important that you now change it to the other equation, and instead of 2 times x, I'm going to put in 2 times 8 minus 3y, okay? Plus 5y equals 13. And I'm going to write that in blue so that you can see, oops, not plus, but minus 8 minus 3y. So you can see that instead of this x here, I've just replaced it with 8 minus 3y because we know that x is equal to 8 minus 3y. So instead of putting x there, I can just put 8 minus 3y instead. They are equivalent to each other. This expression is equivalent to x, so I can substitute it right there because of that equal sign, okay? And I have parentheses around 8 minus 3y because they're all together. So if 2 is being multiplied by x, then I better make sure later on when I multiply by 2, everybody inside the parentheses gets that multiplication by 2 on the outside, okay? So we're going to continue then. So what we did was we substituted 8 minus 3y for x, okay? Just wherever we saw x, we substitute with 8 minus 3y. Now we're going to actually do the work, because now instead of 2 variables, we only have 1 variable left. That was the whole point of it, was to get rid of that pesky x, because we can't do anything when we have 2 different variables, and replace it with a y of an equivalent expression. So now we can do regular math and solve this equation. Okay, 2 times 8 is 16. 2 times negative 3y is negative or minus 6y, plus the 5y, which we didn't touch, equals 13. Now, let's see, I have minus 6y and plus 6y on the same side, so I can combine that. Negative 6 plus 5 is negative 1y, or just negative y. This 16 gets pulled back down here. That negative belonged to the 6, so don't worry about that. That's a positive 16 minus y, because we did the combining like terms over there. 13 gets brought back down. I have constants on both sides. Y, the variable, is already on the left side, so I'll subtract the 16 to have it join the right-hand side. That cancels. Be careful, we gotta keep that y negative, and then 13 minus 16 is negative 3. So I get negative y equals negative 3. We're not done here, because we need to know what positive y, a regular y, equals to. Well, if we know a negative y equals to negative 3, then a positive y has to equal a positive 3. It's just the reverse of it, okay? So y equals 3. We have half of our puzzle already, because remember at the end we need an answer that's x comma y. So far we know that y is equal to 3. So we only have half of our puzzle. Remember, the last step now is to take y equals 3 and replace it in either one of those equations, because if we know y equals 3, we can put it into either one of those equations to now figure out which value x is equal to. I don't know about you, but that first equation that we had chosen to isolate our x sounds good again for substitution. Okay, so this third step that we're going to do is we're going to replace y with 3 to find x. Okay, so we can choose either equation. I'm choosing the first one because it looks like less math. So instead of x plus 3 times y, we're going to put x plus 3 times 3 because y equals 3. So x plus 9 now equals 8. Subtract 9 both sides. So then x equals -1. Okay, so we get that x equals -1, so we have the solution -1, 3. We know it works for the first equation. We could do some quick math on the second equation to just double check that it works. X equals -1 plus 5 times 3, because y equals 3 equals 13. 2 times -1 is -2, plus 15 equals 13. 15 minus 2 is 13, so 13 does equal to 13. Yes, that checks out. And it should check out if we did the math correctly here when we replaced y with 3 to find x. So that's it, and I say that's it in quotes because that's a lot of steps, right? However, when we get to problems where there are decimals and fractions, it is much easier to do it algebraically with substitution rather than busting out a graph paper, ruler, and then sweating over whether you drew a line correctly in order to get the answer correctly. And then at the end, you're like, I don't even know if this is 4/10 or 3/10 because my line might be crooked. Okay, let's do another example then. So in this example, we again are trying to solve the simultaneous equations using the substitution method. Go ahead and pause the video and try it on your own first. Use your steps, see if you can figure it out on your own first. Okay, so remember our first step is we're trying to find the equation that'll help us isolate a variable easiest. And I'm going to choose the first one again because it's 3x minus y equals 7. So I can easily figure out what y is alone. I'm going to subtract 3x on both sides. And remember, they are not like terms, so we're going to keep them separated. Negative y gets let down because we didn't touch it. And then this stays as 7 minus 3x. Remember, we want to know what positive y is because later on we're going to plug it into the other equation and it's a positive 4y. If it was minus 4y, maybe we can get away with keeping as a negative y, but we want a positive y. So we're going to flip everything here. If negative y equals a positive 7 minus 3x, then a positive y is equal to negative 7 plus 3x. So all the signs just switch. And you might want to just rewrite it so that it looks a little nicer. Instead of negative 7 plus 3x, it's 3x, the positive first, and then minus the 7. So all I did right there was I just switched the locations there. Okay. I didn't actually change anything. I just switched the locations. Like that. Okay. So now we get y is equal to 3x minus 7. So our second step, and I apologize for the blatant Christmas colors here. Our second step is now to take that equivalent expression because 3x minus 7 is the same as y. So we're going to put that into the other equation. Instead of y, we're going to put in 3x minus 7. Okay, and I'm also going to write it in green so you can see that, but not too bright of a green. So we're going to write it in green so you can see that that's where it came from. Okay, so 6x plus 4 times 3x minus 7 in parentheses, very important, is equal to 17. And then we're going to distribute that. So the 4 needs to be distributed to everybody inside. And it becomes 6x plus, not 4, but 4 times 3 is 12x. 4 times negative 7 is negative 28 or minus 28 equals 17. I have like terms here. 6x and 12x can become 18x minus 28 equals 17. Then we're going to solve it like a normal two-step equation. I got to add 28 to both sides. So I get 18x equals, that would be 45. 17 plus 28 is 45. And then we're going to divide both sides by 18. And that doesn't look like it goes in evenly, right? So what's 45 divided by 18? Well, 18 goes into 45 2.5 times. All right. I can keep it as 2.5, or I can do 2.5. 2.5 is a very accurate decimal. It's not repeating, so we can keep it as that. Okay, so that's the first half of our answer. That was our x, so we're going to write it first in our ordered pair. And remember, we're not done yet. We only found x, so now we can replace it in either equation. I'm going to pick the first one again because it seems easy. So instead of 3x minus y equals 7, we have 3 times 2.5 minus y equals 7. Or instead of doing all this, you're trying to find y, right? The easier thing would be replacing it back into your equivalent expression right here. Haha. So instead of y equals 3x minus 5, you have y equals 3 times 2.5 minus 7. Sorry, I misspoke. So y equals 3 times 2.5. That's 7.5. 7.5 minus 7 is a half. So you have 2.5 and a half as your answer. That would be kind of terrible to draw out using your graphing method, and maybe you drew a crooked line, so instead of a half it looks like, I don't know, 3/4, right? So this is what y equals. And again, you can check it in both of them to make sure that it works. So let's use our calculator to check it. 3 times x, 3 times our x is 2.5, gives us 7.5, minus our y, which is a half, should get us 7. Yes, it works for this one. Let's try this equation now. 6 times our x, which is 2.5, is 15. 15 now added to 4 times 0.5. 4 times 0.5 should be 2. So we are adding our 15 to that, which will give us 17. So it checks out with both of our equations. So this answer right here, we are very confident that the answer is 2.5 and a half.